Yesterday we looked at resistor noise. Uh, you have noise in a resistor because the random thermal motion of electrons. So if you look at any cross section, you won't have a steady stream of electrons. There will be electrons like buzzing back and forth. And you also know the physical phenomenon from basic physics that electrons collide with fixed atoms in the lattice, go in some random direction, collide with something else. When you say there is a current, there is an average flow in one direction, but instantaneously they will be buzzing around back and forth. Okay. And as far as circuit design is concerned, resistor's noise is well modeled by a white noise spectral density that is constant across all frequencies. The spectral density of the resistor's noise current is proportional to the conductance. The larger the conductance, the larger the noise spectral density, current noise spectral density. Now, of course, this gives the observed result that the resistor's noise has a variance of infinity, because if you do have white noise from minus infinity to infinity, you have infinite variance. That is not true. As I said, this factor kT is really h nu by exponential h nu by kT minus 1, which you see in other physics contexts. Okay, and so resistor's noise is of course actually finite and but noise variance is finite. But because this roll off with frequency, at very high frequencies it goes to 0, but the frequency at which it starts changing is already in the terahertz. So when we are designing circuits at gigahertz, it is quite convenient to simply assume a constant spectral density. Then we'll look at example calculations of what we do with noise spectral densities. Those of you who are taking advanced electrical networks will see a lot more of these noise and related results, how to calculate it in complicated circuits and so on. Okay. I took a simple circuit here, Vi, Vo, and I will model the resistor's noise as a series noise voltage source. I could also model it as a parallel current source with the resistor. Now, what is the transfer function of the circuit? 1 by 1 plus SCR. So this is a low pass filter. Now, what is the transfer function from the noise source to the output? What is the transfer function from the noise source to the output? Same, because this Vi and Vn are really in series. So V0 by Vn is also 1 by 1 plus SCR. Now we know that the resistor's noise spectral density, it is a constant at 4 kTr. What will be the noise spectral density of the output? What is the noise spectral density of the output? What's that? So it is basically this is Vo by Vn. So the noise spectral density at the output will be the spectral density of the noise source times the magnitude squared of the transfer function from the noise source to the output. And in this case, it is this S has to be replaced by J2 pi F, that square, okay, which basically gives you okay. So if you plot the output noise spectral density, it will start with, at very low frequencies, this factor is 1 when f is 0 and very low, compared to 1 over 2 pi Cr, and I will plot it like this. Okay. So this is what happens. So the output noise is also low pass because essentially the capacitor ends up shorting the noise. Okay. So this is the output noise spectral density. What will be the output noise variance of the output noise? It has to be the output noise variance is integral of the spectral density from 0 to infinity. What will this be? Please calculate it if you haven't done it. Please calculate the integral. So this, if you change the variable of integration to 2 pi FCR, essentially you will get and that I won't go through. I am assuming you know how to do this integration, and this will be, huh? There is no, yeah, 2 pi CR. Yeah. No. Which one? Yeah, here, yeah. 2 pi CR. That's right. So this will be pi by 2. So you will get the answer to be kT by C. So the interesting thing is the answer depends only on C and not the resistor, though the resistor is the one that is creating noise. Why does it come out like this? What's that? Yeah, but the amount of noise generated is proportional to the resistance, right? The spectral density. Yeah, so what happens in this case is that if let's say the resistor becomes half the value, and then you will have, let's say, then the spectral density becomes half, but the bandwidth becomes twice as much. Okay, so you will have twice the bandwidth. So the area under this green curve and the blue curve are the same. So that is how we can interpret it. Changing the resistance changes both the spectral density as well as the bandwidth. Okay, and in the same proportion. If the spectral density goes up by a factor of 2, bandwidth goes down by a factor of 2, and you will end up with the same integrated noise. But actually this result itself can be derived from thermodynamics. You can see some derivations of that. It's related to degrees of freedom and the energy per degree of freedom and so on. Okay. So it looks a little bit strange in that the lossless components like capacitors and inductors don't have noise. Okay. But the expression for the integrated noise contains only the capacitor value. And when you look at these results in advanced electrical networks, you will see more of this, and it's also related to the energy stored in the network and so on. It can be related to those things. Okay, there are some fundamental theorems. But for us, essentially we need to know that this is the integrated noise. Okay. So, if you have a capacitor of some size, that limits the noise. The larger the value of the capacitor, the smaller the noise will be. Okay. Now let's say you want to have the same bandwidth. I mean, this function has to be the same, this low pass function, but you want to have half the noise. What should you do? What's that? Yeah, so I have to make C as 2C and R as R by 2. Okay. So this will give me the same transfer function, but it will give me half the integrated noise variance. Okay. The variance is of course also the mean square value. This is the variance and also the mean squared value, and the RMS value would be square root of KD by C. Okay. So now when you make the resistance half and the capacitance twice, what is the price you pay? Area. More importantly, the amount of current that is flowing in the circuit is twice as much. Okay, you will be dissipating twice as much power. Okay, and this is again a fundamental relationship. I won't go into it now. Maybe we'll do it in one of the assignments. So if you have to lower the thermal noise, this is known as thermal noise, this noise in the resistor, you have to increase the power dissipation. Okay, this is a fundamental result, and this also relates to circuit scaling that we'll see. Okay. Now just to get familiar with some values for a 1 picofarad capacitor, how much is the RMS value of noise? Can you calculate it quickly? What do you get? Huh? 2 nanovolts. I mean, assume room temperature if we don't specify anything. Yeah. So KT is 4 times 10 to the minus 21 and C is 10 to the minus 12, and this is many volts, so the units have to be correct. So this is square root of 40 times 10 to the minus 10 to the minus 5, right? So basically this gives about 60 or 63 microvolts. Okay, it's small but not overwhelmingly small. I mean, if you, so this, you need to have, as engineers, you need to have some ideas about numbers also. Okay, just like yesterday I mentioned that the noise spectral density of a 1 kilo ohm resistor is 4 nanovolt per square root hertz. The integrated noise across a 1 picofarad capacitor in this context is 63 microvolts. Okay. Now this, by the way, this result, it is 4 kTr, and this whole number now, this is what are the dimensions of whatever I have in brackets here? Huh? What is it? Yeah, what is 1 over time? Frequency. Okay, so it is the spectral density, which is volt square per hertz, times the bandwidth, the effective bandwidth. Okay, so if you took a noise source and let's say it had wide noise spectral density of S0, and you pass it through a brick wall filter of bandwidth FB. Okay, so that is the input noise spectral density is S0, the output noise spectral density will be the same thing but limited abruptly to a bandwidth of FB. What will be the variance of noise at the output? It's the area under the spectral density, right? So it is S0 times FB. Now in our case, we don't have an abruptly cutting off filter like this. We don't have an abrupt filter like this. We have something of this sort, and the integral under that turns out to be, so this part here, this is what you would call the 3 dB bandwidth of the low pass filter, right? 1 over 2 pi CR. So this is FB of the low pass filter, or let me call it FBW, 3 dB bandwidth of the low pass filter. We should call it F minus 3 dB. So the spectral density gets multiplied by pi by 2 times F minus 3 dB. It is a little more than the 3 dB bandwidth because we don't have an abrupt cutoff at the 3 dB bandwidth, but we do have content beyond that. Is this okay? And this is known as the noise bandwidth of a first order low pass filter. This is a first order low pass filter, right? Is this okay? So you can do this for any other filter also. You can essentially represent, let's say the input is white noise, the output will have some spectral density, and if you integrate it, you will get some variance. Now you imagine a brick wall filter that will give you the same variance. So the bandwidth of the brick wall filter is the equivalent noise bandwidth of the original circuit for which you are calculating. Okay? These are terms that you may see, so you should be familiar with them. So similarly, if the capacitor becomes, let's say, 10 femtofarads, then this 63 microvolts becomes how much? If the capacitor is 10 femtofarad instead of 1 picofarad, what's the integrated noise? How much? Why 20 micro? Huh? Divided by? Well, you divide it and tell me, right? I mean, yeah, it's just 10 times larger, right? The capacitance has become 100 times smaller. So the noise is 10 times larger. So this is 630 microvolts or 0.63 millivolts. Okay. This is just to show you the orders of magnitude of noise that can be there with this. Of course, in a circuit you have many more noisy components. You can have a lot more noise than this. Is this okay? So this is about resistors noise and some basic noise calculations. And if you have a circuit with many resistors, you can model the noise of each resistor. Maybe you can also model some of them with current and some others with voltage. And so on. Okay? And you find the transfer functions from, let's say the output is a voltage somewhere, you can find the transfer function from these things to those things, and it will be the noise spectral density of IN1 times HO1, that is from IN1 to the output, plus the noise spectral density of VN2 times HO2, which is the noise spectral density from the second source to the output, magnitude square, and so on. You go on adding. These are all different resistors, physically different resistors, so their noises are uncorrelated, so you simply add the spectral densities. Okay? Now if you have only resistors and capacitors or resistors and inductors in the circuit, you will see that there are easy way of calculating the noise. But then our circuits can also have other components which are noisy as well. Okay? Any questions here? Now just like the other noisy components that you will frequently encounter is the MOS transistor. A MOS transistor also has thermal noise, and in fact a MOS transistor looks something like a resistor, right? It is nonlinear, that's all. So you first create a conducting channel by applying a voltage beyond the threshold voltage. That creates a channel between the drain and source. It's essentially a resistor, and with the gate voltage you can control the resistance, and with the drain source voltage you can control the current flow. That's how it is. Okay. So now the current in the transistor is given by square law. I'll first write it down for saturation region. ID is mu Cox by 2 W by L VGS minus VT square. This is sort of the zeroth order, very basic model. This is true when VGS is greater than the threshold voltage, that is the transistor is on, and VDS is greater than VGS minus VT. Now, as with a resistor, if you manage to look at the instantaneous current going through this, it will not have only this part, but it will also have wiggles due to due to thermal motion of electrons. Okay. So then the actual current can be modeled by this current plus some noise current. Okay. So essentially it's an additional source, right? And the spectral density of this noise current is again in saturation region. For the long channel transistors that follow square law, it can be shown to be 1/3 kT times Gm, where Gm is the transconductance of the transistor. Okay. You can notice the similarity between this and the spectral density of a resistor's noise current, which is 4 times kT times G, where this is the conductance. So instead of the conductance, you will get the transconductance, and then instead of 4, you get 8/3. That I'll quickly show where that comes from. You may have seen this already. Okay. This is in saturation region. Yeah. Okay. Yeah, so noise is always small enough. We consider it to be small enough to be a small signal. Okay. Yeah, I mean kT you already know, right? It will always appear together. kT is 4 times 10 to the minus 21. So, yeah. Anyway, it will probably be there in the exam paper, but that's an easy enough thing to remember. So again, all you have to do is in your small signal model, again, what he said was quite important. Noise we always treat as small signal. It is small. Okay. Although the white, this is a white spectral density, right? This, by the way, is known as thermal noise. In case of a MOS transistor, there are other types of noise also which we will see, but this is thermal noise, similar to what happens in a resistor. And its spectral density is white, which means it is constant over all frequencies. Now again, if you assume that and you calculate the variance, it comes out to be infinite. But in reality it is finite, and it is legitimate to treat it as a small signal and use small signal analysis in your calculations. Okay? Is this fine? Now, if we go to the other extreme, let's say we bias it with VDS equal to 0, but with VGS greater than the threshold voltage, the MOS transistor will be on, but it will be in triode region. Okay, it will be in deep triode region actually. And if VDS is 0, this is the drain, this is the source, this is the cross section of the MOSFET I am drawing here, and this is the gate. And if VDS is 0, the channel will be symmetric. That is, in the sense it will look the same all the way from drain to source. Okay. Now, let me show it like this. This is for VDS equal to 0. And if you apply VDS, I think this again, those of you who have done device physics will know. If you apply VDS more than 0, what happens is the charge density is smaller at the drain than at the source. It becomes asymmetric. Now at VDS equal to 0 at least, it is exactly like a resistor, right? So this inversion charge here is like a slab of conducting material, and it is like a resistor. Okay. So what do you expect the noise current to be? The spectral density of noise current, what do you expect at least at VDS equal to 0? 4 kT times what? Yeah, it's 4 kT times GDS. This is GDS in triode region, that is GDS at VDS equal to 0. Okay? Is this fine? So is this going to be more or less than the noise here? What is the expression for GM in saturation region? Using the zeroth order model, what is it? Mu Cox W by L VGS minus VT. What is GDS in triode region, especially at VDS equal to 0? What is it? Half? Yeah, it is the same thing, right? At VDS equal to 0, it is the same thing. You will have another like minus VDS as, but at VDS equal to 0, that goes away. So actually this part is the same. I mean this factor, only you will get 4 instead of 8 by 3. That's all. Okay. Now according to the basic square law model, the GDS at VDS equal to 0 is the same as GM in saturation region. Okay. Is this fine? So now actually there is a unified model which we don't use while doing circuit design. In fact, while doing circuit design, we will assume that it's either in deep triode region where it's behaving like a resistor, or more often it's in saturation region where it's behaving like an amplifier. So then the noise spectral density is proportional to the transconductance of the MOS transistor. Okay. But there is actually a clean expression which works in all regions. It turns out to be so this is the inversion charge density. Okay. Sorry, inversion charge actually, not inversion charge density, the inversion charge. Okay. So that modulus appears because the inversion charge can be positive or negative, but here you have the positive number. How many of you have done devices course? All of you? Okay. So what is the expression for inversion charge? How much inversion charge is there in a transistor? Huh? Cox? VGS. What's that? No, no. Inversion charge means the mobile charge, right? Not the, you don't include the depletion charge. So what is that? No, no, that's not the charge then. How much is the MOS transistor is a capacitor, right? So what is the charge across, what is the charge on the plates of a capacitor? Yeah, it is, I mean, in a capacitor, the charge is the capacitance times the voltage. Now, what is the effective voltage across the MOS capacitor? VGS minus VT. Okay. In fact, that's the meaning of the threshold voltage, right? When you apply VGS more than VT, that's when the inversion layer starts forming. And the inversion layer charge is proportional to VGS minus VT. And how much is that charge? Huh? How much is it? What is the expression for the amount of charge? Yeah, Cox into area into, yeah. So it is basically Cox times WL times VGS minus VT. In which region is this? This is in deep triode region when you have uniform inversion layer charge for all the way from source to drain. So if you substitute that, what do you get? You get 4 kT times mu Cox W by L VGS minus VT, and this is basically the same as this one. Okay. This is at VDS equal to 0. What is the inversion charge in saturation region? Will it be the same or different? Different. What is it? It's actually 2/3. It comes out to be 2/3 Cox W by, W times L VGS minus VT. In the device course, did you look at the capacitance of a MOS transistor? What is the value of CGS in saturation region? It's 2/3 Cox WL, right? So this is where the 2/3 comes from. Essentially, the charge here, it is uniform. It's actually like very much like a capacitor. Here, you see that it is like a capacitor, but the charge on the left side is a lot more than the charge on the right side. On average, if you take it, you can show through calculations that it comes out to be 2/3. Okay. So this will give you that 1/3 factor we saw. But we won't be using this for calculation. We will mostly use the saturation region expression everywhere. Okay. So this is the thermal noise spectral density, the spectral density of thermal noise current in a MOS transistor. Okay. Is this fine? Okay. So now let's quickly do an example, work out an example. So let's assume that this is in M1 is operating in saturation and has a transconductance Gm. This is a common source amplifier. I assume that it is biased correctly. I am not showing the biasing details, and I have the small signal input here. Again, don't assume that this is the full picture. The small signal input is here. I have biased it somehow. Don't worry about that now. And this is RL, and this is the output. So first find the noise spectral density at the output, and secondly, if you load the output with a capacitor C, find the integrated output noise, which means variance. Okay. Okay. What? How did you get this? No, is the transistor the only thing that does noise? So just do this systematically, right? So we have Vi, and the transistor model is just Gm. This is VGS, that is Gm times VGS, and we have the, first let me ignore the capacitor, or I can also include it, it doesn't matter, RL. Then how many noise sources do I have? I have the IN1, which is the noise current of the MOS transistor, and in this case it makes sense to model the noise current of the resistor also with a current source, and let me call that IN2. Okay, and I can also include this load CL as well, or C. This is possible. So now I need to find the transfer function from these currents to the output voltage VO. And what do you do with the input voltage? 0. So once the input voltage is 0, this is like really elementary circuit analysis, and this current source becomes an open circuit. So all you have is these currents will flow into the load network, whether it is a resistor or a resistor in parallel with a capacitor. Okay. So if you have only a resistor, or if you include the capacitor also, it will be this will be the transfer function. Okay. So the output noise spectral density then is, it is SIN1 times V0 by IN1 square. I am just showing you step by step. So if you are getting mixed up somewhere, it's always good to go back to the basics. SIN2 times the second transfer function square, which is basically 8/3 kTgm times RL square plus 4 kT by RL times RL square. So basically this comes out to be, you can write it in a couple of different ways. So if I take 4 kT RL out, I can write it as 4 kT RL plus 1 plus 2/3 times GMRL. I can also take the other one out. Let me do it like this. There is a particular reason. 8/3 kT by Gm so this is basically the first term, right? And I can also write this as 3/2 Gm RL. Okay, it's the same thing. I have just written it in a slightly different form. Okay, this is excluding the capacitor. If I have the capacitor also, instead of RL, I would have, so this factor here, right? So I would have 8/3 kT Gm plus 4 kT divided by RL times, instead of RL square, I would have the magnitude squared of this, which is RL square by 1 plus okay. Now if I don't have the capacitor, the integrated noise is of course infinite, but if I do include the capacitor, what will be the integrated noise? I mean, we got some results now, right? What is it? So the integral of this part, I mean excluding the RL, that is the only part that's dependent on F here, right? What is that? How much is that? Yeah, 1/4 RL times C. Okay, so that you can just multiply, or essentially it is pi/2 times the noise bandwidth in hertz. Okay. By the way, whenever you do these quantitative calculations, while doing circuit analysis, you invariably use Laplace transforms for circuit analysis, and this S corresponds to j omega, where omega is in radians per second. Now the spectral densities are invariably expressed in most cases in terms of hertz, the cyclic frequency. Okay, so all those scaling factors have to be correct. Otherwise, it's very easy to mess up by factors of 2 pi when you do these calculations. Okay. So again, I'm just showing it. This is overly detailed for a simple circuit like this, but you find out the transfer functions from every noise source to the output, and then you multiply the individual noise spectral densities by the corresponding magnitude squared of the transfer functions. Okay. Is this fine? So the output noise spectral density will also be low pass, and sigma VO square is 8/3 kT GM plus 4 kT by RL times RL square 1 over 4 RL times C. Okay. So you can simplify this and put this in different forms. Okay. So obviously both the MOS transistor and the resistor contribute to noise. Now this is an amplifier, right? So we want to, this is what we have designed. So in that case, which one contributes more noise? Is it the MOS transistor or the resistor? MOS transistor. How do you tell? So if you look at this form of the expression, you can, so this is from RL and this is from M1, and it's an amplifier, so we expect GMRL to be more than 1, hopefully substantially more than 1. Then if it is high gain, then the MOS transistor's noise dominates. Or again, in the bottom I have written the same expression in a different way. This is from the MOS transistor and this is from RL. The one from RL will be smaller. Okay. Now this is in general true. Here we have only two components, a MOS transistor and a resistor, but you could have a chain of amplifiers. If you do have a chain of amplifiers, it's usually the first stage that contributes the most noise effectively, and the relative contribution keeps going down as you go down the chain. This makes sense in a way in that even if you have identical amplifiers, let's assume that you apply a signal, it gets bigger and then bigger and bigger. So the effect of the last stage will be lot smaller than the effect of the first stage. Okay? Is this fine? Now we won't deal with the other non-ideal feature of circuits, that is distortion. The nonlinear distortion, it's the other way around. Okay? So the signal is small, it keeps getting bigger and bigger. As the signal gets bigger, that's when the transistor or any nonlinear circuit gets driven into the nonlinear regions. Okay? So for distortion, it is typically the later stages that matter more, and for noise, it is the earlier stages that matter more. Okay? Is this fine? Now let's do one last thing with this, and after that we'll continue the discussion later. So let's say that, I know that there are two noisy components here, the transistor and the resistor. Okay? And in the actual circuit, the many other circuits that you analyze may have many more components. So I can of course do the analysis and then find the noise and so on. Now let's say you build the amplifier for somebody else. You don't want to ask them to analyze everything. So let's say I want to specify a source here. I'll assume that it's a voltage source. Okay. Now the idea of this source is that this should include the effect of the noise from every component in the circuit. What I mean is the following. So let's say you imagine you have your regular circuit with its noisy components, it will give you some noise output. Now imagine that you have a circuit with this input Vn in and a noiseless version of the same circuit. That should have exactly the same output noise. Then you can say that this source here encapsulates the effect of all the noise in the circuit. And it's a useful thing to have, because once you have designed it, as a designer you have to worry about like every noise source in the circuit. but the user doesn't have to go into the insights, right? They may not even know what the inner details are. So for them, this is enough. This is like a noise specification. And it's also a useful thing because now you can see that you have Vi and this noise source gets added to it. So it's easy to directly compare the relative magnitudes of Vi to the input noise source to see whether, to calculate the expected signal to noise ratio. Okay. So before tomorrow's class, please calculate what this Vn is. When I say what Vn is, it's a noise source, so you have to calculate its spectral density. Okay. Please do that.